here, and today in this video we're going to tackle about generating number patterns using modular sequences, especially in Fibonacci mod n. So have you ever looked at a clock and thought about hidden patterns inside it? It's 10 o'clock now. What time will it be in 5 hours? It's 3 o'clock, right? What about in 17 hours? Well, that is also 3 o'clock. So this simple everyday idea, the cycle of a clock, is the gateway to a powerful world of number patterns, a world where numbers don't stretch on forever in a line, but instead moves in a circle. Today, we're going to explore this through modular sequences and discover the beautiful music numbers when they start to repeat. Now, I'm going to introduce to you a modular or the modular sequence. So first, what is modular sequence? A modular sequence is a simply list of numbers where we're only interested into the remainders with respect to our modulus. Now, let's create a sequence. So our sequence here is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. So a modular sequence is simply a list of numbers where we're only interested in the remainder with respect to our modulus. So if we take the sequence of all whole numbers and look at them modular or modulo 5, we get this repeating pattern. So 0, 1, 2, 3, 4, and it repeats to again 0, 1, 2, 3, 4, and it gets back to number 0, or it gets back to 0, 1, 2, 3, 4, and so on. So it is a cycle. So this is the most basic modular sequence, but real magic happens when we apply a rule to generate our sequence. So that is the example of our modular sequence. Now, in this part, we're going to tackle about the Fibonacci or Fibonacci sequence, modulo m or modulo n. So what do you mean by Fibonacci or Fibonacci sequence modulo n? So Fibonacci sequence modulo n is an excellent idea because it creates one of the most beautiful and surprising patterns in all of mathematics. It is also called the Pisano period. Now for Fibonacci sequence, it starts with 0 and 1. And then the sum of each new number, or each new number is the sum of the two before it. So before 0 and 1 is equal to 1. And then the sum of new number before it, 1 plus 1, is equal to 2. And then 2 plus 1 is equal to 3. And then 3 plus 2 is equal to 5. And then 5 plus 3 is equal to 8. Again, 8 plus 5 is equal to 13. And 13 plus 8 is, we all know that it is equal to 21. And 21 plus 13 is equal to 34. And then 34 plus 21 is equal to 55. And it keeps getting, or it keeps growing seemingly without end. But what happens when we apply our modular lens? So let's see what Fibonacci modulo n looks like. So for this example, we have modulo 3. So we have here, we have generated this sequence. For our example, f of n modulo 3. So f sub 0 is equal to 0. So our sequence is 0. F sub 1 is equal to 1. X equal to 1. So our sequence is 0 and 1. And for as I have said earlier, Fibonacci is the sum of two numbers before it. So f sub 2 is basically 0 plus 1. As you can see right here, f sub 2 is the sum of two numbers before it, so 0 plus 1 is equal to 1. So we have here our sequence 0, 1, 1. F sub 3 is equal to the two numbers before it, F sub 3. So 1 plus 1 is equal to 2. So our sequence right here is 0, 1, 1, and 2. And for F sub 4, we have 2 plus 1 is equal to 3. And 3 modulo 3 is equal to 0. So we have our sequence right here. So 0, 1, 1, 2, 0. And if we continue our sequence right here, we have a pattern that we have made a pattern. So if you noticed, our F sub 4 is equal to 2 plus 1 is equal to 3 is equal to 0 because 3 modulo 3 is equal to 0 because 3 divided by 3, or there is no remainder. So if we continue and also if you noticed here, we have a pattern like 0, 1, 1, 2, and then it gets back to 0. So if we continue, F sub 5 is equal to, so if you notice, this is 0, and again the Fibonacci is the last, or the sum of the last two numbers. So we can continue this. So 2 plus 0, so we can write here 2 plus 0 is equal to 2. And for our sequence, we have 2. So as you notice, 0, 1, 1, 2, 0, and then it gets back to 2. And then if we continue, F sub 6 is equal to the last two digits, which is the 0 plus the 2 is equal to 2. And for sequence, this is 2. And then again, F sub 7 is equal to last two digits, which is 2 plus 2 is equal to 4. And if we divide by 3, because our modulo is 3, it gives us one remainder 1. So sorry, so our remainder here is 1. So if we continue it again, F sub 8 is equal to the last two digits, which is 2 plus 1, sorry, this is plus sorry, is equal to 3. And again, our 3 is equal to 0 because 3 divided by 3 is equal to 1, or 3 modulo 3 3 modulo 3 is equal to 1, and there is no remainder, so that means this is 0. And then F sub 9 is equal to, again, the last two digits, which is 1 plus 0 is equal to 1. And for our sequence, this is 1. So if you notice, this is the pattern that we have made for f of n modulo 3. So this is the pattern right here. So we can rewrite our pattern, which is 0, 1, 1, 2, 0, 2, comma 2, 1, 0, and then 1, and so on. So this is the Fibonacci sequence of f sub n modulo 3. So does that look familiar? That's how we started the sequence. This is a huge deal because the rule for Fibonacci only depends on the previous two numbers. If we ever see a 0 followed by a 1, again, the entire sequence must repeat from that point forward. So the Fibonacci sequence modulo 3 becomes 0, 1, 1, 2, 0, 2, 2, 1, 0, 1, 1, 2, and so on and forever. So this is the repeating cycle, or this repeating cycle has a name, and it's called the Pisano period. And here's truly magical part. No matter what modulo M you choose, the Fibonacci sequence will always become periodic, whether it's modulo 2, modulo 10, or modulo 1000, the finite or the infinite. Growing Fibonacci sequence collapse into a perfect finite cycle. So for now, let's generate another problem or another sequence. For example, right here we have f sub n modulo 4. So for example, modulo 4. So again, for every Fibonacci sequence, we should start, or we must start from 0 to 1. So f sub 0 is equal to 0, and then for the sequence this is 0, and then f sub 1 is equal to 1. For sequence this is this is 1. So we have two numbers right here, and we must add these two numbers so that we have our sequence. So f sub 2, because this is 0, 1, and 2, is equal to the first two digits that we must add. So this is 0 plus 1 is equal to 1. For sequence this is 1. F sub 3 is equal to, again, the last two digits, which is here 1. So this is 1 plus 1 is equal to 2. For the sequence this is 2. Alright, so f sub 4 is equal to, again, the last two digits, which is the 1 and 2. So we should add that 1. 1 plus 2 is equal to 3. For sequence this is 3. This is f sub 5 is equal to last two digits 2 plus 3 is equal to 5. And then if we divide 5, or if we divide 5 divided by 4, we have 1, which is we have 1 remainder 1. So our remainder right here is 1. So as you can see, we have our sequence. So let's continue. So f sub 6 is equal to, again, the last two digits, which is 3 plus 1. So 3 plus 1 is equal to 4. And if we divide 4 by 4, we have no remainder. So this means that this is 0. So again, continue. F sub 7 is equal to, again, the last two digits, 1 plus 0 is equal to 1. For sequence this is 1. F sub 8 is equal to 0 plus 1 is equal to 1. For sequence 1. F sub 9 is equal to last two digits, 1 plus 1 is equal to 2. Sequence this is 2. F sub 10, 2 plus 3, this is 1, is equal to 3. For sequence this is 3. F sub 11 is equal to 2 plus 3 is equal to 5. And if we divide that 1, this is 1, because our remainder. F sub 12 is equal to 3 plus 1
is equal to 4, and there are no remainder because 4 divided by itself, there are no remainder. So as you can see, we have our sequence right here. So the sequence of f sub n modulo 4 is equal to 0, 1, 1, 2, 3, 1, 0, 1, 1, 2, 3, 1, 0, and so on. So that's it right here.
So if you can see, this isn't just a mathematical curiosity. This property is used in computer science to generate pseudo-random numbers efficiently, and even helps mathematicians find giant Fibonacci numbers without having to calculate all the digits. So modular sequence, especially in Fibonacci sequence, teach us a profound lesson. Within the apparent chaos and infinite growth of numbers, there is a hidden predictable order. By wrapping the numbers or the number line into a circle, we don't limit numbers, we reveal their essential rhythmic nature. So next time you glance at the clock, remember you're looking at one of the most powerful ideas in mathematics. So I hope you have learned something in today's lesson. And that's it. Thank you guys for watching.